All right, let's get started. So today we're going to continue our discussion of mobile phone security, and we're going to turn our attention from the device security angle, which we talked about on Tuesday, now talking more at the application layer about the security of actual applications running on these mobile devices. And to set the context, why these sort of smartphones have a different operating system and why they look so different from a typical computer, it's good to understand what their goal is in designing an operating system. So the goal for these phones is to make it so that users can actually run applications from any developer. So this is not quite how you might actually have or make it safe maybe, to be precise, to make it safe to run applications from any developer. And on a desktop machine today, it's a little bit of a questionable thing to install some random software that's on a suspicious website on your machine. You might not actually do this. But the goal for the smartphone operating systems was to actually make it possible for users to install apps very much like you would visit a website. So you probably don't think twice about visiting some funny website because you're pretty sure the browser will not let your computer do anything too bad if you visit a suspicious website. And the goal was to make installing an app almost the same level of security decision as visiting a website. And part of the reason for this was to make phones actually much more capable. So at the time Android and iOS were being designed, this would have been 15 years ago or so at this point, there were already smartphones that ran arbitrary applications, but one example would have been like Windows CE was an operating system that looked just like Windows on a smartphone. And you would just install Windows apps, and there was like all the same directory structure you'd have on a Windows machine. It was all shared, and you wouldn't actually install arbitrary apps. That was a bad idea, very much like it would be a bad idea to install some suspicious software on your Windows machine. So the developers of sort of Android and iOS phones decided, it's going to be much more powerful if our phones can run lots of software, then people will actually want to use our phones because there's something useful to run on them. So the security was a big goal for them because it enabled a broad range of applications that made their phones more useful. And of course the threat that we're sort of implicitly talking about here is that the application might actually access user data. Maybe corrupt it or steal it, leak it off your phone, or maybe sensors, maybe like listening on your microphone or looking at your webcam. These are all bad things that could go wrong if you install the wrong application. And this is sort of at a high level, maybe at the more specific technical challenge level. The hard thing here for the designers of these operating systems was to really reconcile having isolation and sharing at the same time. So we'll look into exactly what this means in a second, but roughly speaking, we kind of know how to isolate, but you want a fair bit of sharing on your device, and sharing causes these kinds of problems where an application might now have access to your data. All right, so we'll look at, I guess, you guys all read the paper. Android is a pretty good case study of this. Android and iOS in many ways look the same. So many of you guys asked, iOS is all about hardware security, this is all about software security. I think to a large degree, this is where the papers focus on. And as I mentioned, the Android phones have secure enclaves and secure boot, much like iOS devices do. And iOS has a plan kind of like what we're going to talk about today. But in some ways, Android is a little bit less restricted and more open. So Android takes this goal of running apps from unknown developers to a sort of more extreme point, if you will. You can install much more different kinds of software on Android devices, and they rely more on technical measures for security rather than some perhaps less precise technical measures that happen for iOS. In terms of the end security, not super clear, but in terms of ideas, Android, I think, has a more coherent, clear security set of techniques and plans. All right, hopefully that made some sense. Ask questions through Kevin or directly if you are fuzzy on anything. But I wanted to start maybe by sort of contrasting some extreme endpoints. So we keep mentioning desktop operating systems. as one point of comparison, but good to try to understand how this all works. So on a desktop operating system, right, so you have your operating system, and underneath you have your file system storing all your data. So on a desktop OS, what it means to run applications is that you just have a bunch of processes running in your machine. But there's no isolation between these applications, so they can all access the same set of data. This is super convenient in many ways, right? So sharing is easy. So you can pull up any application on Windows or on Mac OS, and you can open any file you have on your computer. This is great. I have a C file on my Linux machine, let's say. I can use Git to check it into a Git repo. I can use GCC to compile it. I can use VI to edit it. These are all different applications, but they're all accessing the same data. So that's a super powerful thing to do. Same thing for, I don't know, video processing. I can use Photoshop to process a video or whatever other software you might use. I can use other applications to reformat it, re-encode it, upload it, download it, use it with Dropbox. All of this works fantastically well, all because they can all access the same set of shared files in your file system. The applications aren't really very separate from each other. Of course, the downside, from a security point of view, is there's no isolation between applications. So you install a bad app, you're in for a bad time. One example this paper brings up often is ransomware, which is a kind of malicious software. I guess if you install the wrong application, it can just take all your data and delete it or encrypt it in some way that you won't be able to access anymore. That's one example of a failing from not having isolation between apps. That make sense? All right. The other extreme, of course, is if you want very strong isolation. So we kind of know how to isolate things. So we've talked a lot about isolation mechanisms so far, and there's actually systems people have developed that will run different parts of your desktop environment in different virtual machines. There's a pretty popular system called Cubes, for example, or whatever other VMM you want to use. You can Google Cubes. It's a fairly nice piece of software. But what it does is it runs applications in separate VMs. So here you have one application VM. Here you have another application in a VM. But by virtue of running in VMs, what you end up with is each one of them has their own virtual disk, roughly speaking. And this is kind of why security works well. They can't mess with each other. If you install some malware on top of such an isolated system, you're in good shape because it can't access the disks of other VMs. But at the same time, this is not a good place to be if I want to use the same piece of data in multiple applications. Like if I have one VM with Git and I clone my Git source code here, now I have another application with GCC. How the hell do I compile the code I checked out from Git? I can't. That's a slightly ridiculous situation. Same thing with editing it with an editor or writing a paper with a spell checker, then formatting as a PDF. If these are all different applications, there's no way I'm able to share the data. So on an end user device, sharing turns out to be pretty important. Make sense? Questions? All right. Hopefully you guys have a good understanding of what goes on a desktop operating system now. All right. So Android's job is to really figure out how to reconcile these two problems. And it's an interesting case study. So we'll go through how Android works, and it'll hopefully give you some appreciation of what does it take to, of course, start from an isolation plan and then introduce careful sharing without giving up the security properties. So, of course, we're going to start with some kind of isolation so that we have security. And then Android is going to introduce various forms of interaction between applications and the data to enable the kinds of sharing patterns users might want on their devices. So we'll try to take various angles looking at Android apps and understand what they look like. So one way is to understand, I guess, physically, what does an Android app look like? So Android ends up being, at the bottom, it's just a Linux kernel in many ways. Well, it really is a Linux kernel with some small changes from Google, but not super important. So it's just a Linux machine on my phone running Linux. And each application is, of course, a process or could be multiple processes if the application wants to run many processes. So here's another app2. Maybe there's 2 processes in here, process 2 over here for that application. And the way the Android system keeps these applications apart is that it abuses, if you will, the user ID mechanism in Linux. And typically that's used for different users, but on your phone, these user IDs are used for different applications. So it might be the case that application 1 runs as user ID 1001, and application 2 runs as UID 1002. All the processes of this application are going to have that UID. All the processes of this guy are going to have a different UID. That's how Android configures the kernel to keep the applications apart from each other. And for every application, they have their own data directory. So there's probably a directory in the kernel on the file system /data/app1, and the application has access to that. And the kernel also has /data/app2. And only this application has access to those files. And applications can't touch each other's files directly. So far it's looking like a strong isolation plan. There's one other part of the story that's worth sort of understanding. Where do apps come from, and what do the apps look like on disk? So apps in Android are stored in these APK files. So you might have a directory /app on your phone that stores all your app definitions and the code. So, here's might be in foo.apk. That's just a file in your phone. So what's in this file? Really, it's just a zip file with a bunch of contents. The contents is, of course, the application code. So you might have Java code or native code for running in the app. There's in some ways, Java is special in Android. We'll talk about maybe to some degree to what extent that's true. But the security plan really relies on Unix process isolation, user IDs. So security really relies on user IDs. And as a result, an app can run non-Java processes just fine, and the kernel will still isolate them. So you can run arbitrary ARM code on an ARM phone. If you have an x86 phone, it'll let you run arbitrary Linux x86 programs as well. The other part of one of these APK files is what's called a manifest. We'll look at these manifests in a bit, but they define some security properties for an application, what permissions the application needs, what interfaces the application exports for other applications to use, etc. And the last part is the whole thing is signed by the developer. So there's a signature from some developer's signing key that takes this whole APK and proves that it really did come from this developer. Make sense? So this kind of looks like a fairly similar looking isolation story to this. Every app is in its own little world with maybe some details using the OS instead of virtual machines. Make sense? That's how apps run. Questions so far? Yeah?
Just a question more on the trust between Android, the user, and the developer. They talk about consent. And that to me, I felt like it was a very easy factor for social engineering, right? Like, not all developers can be good if you're not vetted necessarily.
Okay, so the question is, so this paper makes a big deal about this whole consent story and what happens if someone is not trustworthy in this plan. So I don't know to what extent this consent story is really how they thought about this security plan from the beginning or not. In many ways, I feel like this is a retrospective paper that was written 15 years or maybe a little bit less after Android was designed and deployed. So maybe they try to generalize it as consent. I'm not sure if that's really quite how they drove it to begin with. And one notable thing is consent doesn't actually mean trust. So they absolutely don't want to trust the application developer. So all these consent stories that they explain in the paper, if you will, are really relative to a particular application or a user. So an application is always able to screw itself over. User can screw themselves over. Same with Android framework. So, if you have a bad application, it can certainly give consent to do things with its data that maybe a normal application wouldn't. But ideally, it only has access to data that's not terribly interesting anyway. Or maybe the user had a bad judgment call. Like if you install a Notepad app that turns out to be a bad note-taking application, and you enter lots of important secret notes into it, well, nothing's really going to help you, man. Yeah, Android doesn't have a plan for saving you there. But to the extent that each application has data that it's trusted to manage, then it can do it. Yeah. Question? Yeah, so the manifest file, we'll talk about this in a second, but roughly speaking, the manifest describes how the application wants to share data or interact with data with respect to other applications, and specifies some security rules about how that application's data should be shared and what privileges that application might want to have with respect to the rest of your system. We'll dive into that in a second after we look at exactly how this sharing machinery works, but you can think of the manifest as largely being all about defining the sharing plan for an application at the top level. Was there another question somewhere here in the middle? No? Ah, yeah.
There's like two tabs on the board. There's data/app1 and there's app1.
Yeah?
The application code typically stored under the same data.
No, actually, okay, so your question is, okay, there's the application data and the application APK file. The APK file is actually not writable by the application. It might not even be readable, I'm not sure. Actually, probably it might not even be readable, not super clear. Depends on the phone configuration. But indeed, an application can't actually corrupt its APK file. So there's a fair bit of design here that prevents a confused application from screwing itself up too much. So for example, it would be bad if your application got really corrupted and corrupted its own code, and at that point, whole thing is just busted from forever. But no, so the APK file is handled by the system, and the application cannot modify its code. So if you reboot, you'll get a clean application. So the system manages that for you. That's one example. Yeah?
What is the problem of signing by the developer?
Yeah, so why do we bother having the application signed by developers? Any guesses? What does this give us? Yeah? Yeah, exactly. Good point. So the reason for signatures, or the main reason for signatures, is so that you can authenticate future versions of the software. So when you first install an application, there's no a priori reason why you should trust this application. Like, you don't actually know whose application you're installing necessarily. You go to the phone, you search for, a flashlight application, you install something, and from that point on, Android actually latches on to the key of the developer that the app came from. So you might have had good or not so good reasons to install the app in the first place. Once you install it, though, you know that it will only be updated by new versions from the same developer. So however you figured out who the developer was to begin with, that's what you get. Now, it's not clear that, well, you have to really go out of your way to install the right application in some ways. So, like even I'm guilty of this. When I need to install the application for my bank, I just go and search for, Citi Banking App Android. And I probably install the first hit on Google, which, isn't defined to be necessarily the right application. But relatively few systems give you a trustworthy path to how to get the right banking Android application for their system, for example. So there are certainly problems there, but at least it's compatible with, if my bank was very careful, gave me a link, like here's the exact Android app you should install, then I install it from the bank. From that point on, even though the updates come not directly from the bank, but through Google or through other ways, it'll only get the right updates from that point. Make sense? Questions? Back there? Yeah? So, okay, the question is, what if the developer buys this application? So, well, you better buy the secret key to sign it, otherwise you haven't bought very much. So probably what it would mean is if you want to sell your Android application to someone so they continue developing it, well, they'd probably expect you to hand over your signing key. So at that point, if your signing key is used for many applications, you're kind of in a pickle. Now you have to either sell all of them or none. So maybe you should use a separate key for different applications, depending on what you care about. Yeah. Other questions? All right. So let's look at what the sharing plan is on top of this isolation plan. So to share between applications in Android, the Android framework comes with sort of an intermediary process that's going to help with the sharing. So of course there's still the Linux kernel underneath. That's providing isolation because we configured it with UIDs. But then if we have one application that wants to share with another app, all the sharing is going to go through this process called a reference monitor. So this reference monitor is going to interpose on all the messages. So if one app wants to do something with another app's data or send something to it or interact in any way whatsoever, they're going to send a message first to the reference monitor. And the reference monitor is going to decide, where should this message go? Is this even okay? Is this allowed? Etc. And then it's going to forward it on. So it's going to forward it on to another application. And the way Android sort of structures these messages is that messages are sent to what's called a component inside of an application. You can think of it as like a path inside of an application or a port number inside of an application, just a way to demux where messages go inside of one app. You can have multiple components in one app. And typically, this is one place where Java comes in. These components are designed to interact particularly nicely with Java classes and methods. So the reference monitor sends a message, and there's a standard library written in Java that takes these messages and sends them to the appropriate component in your application's Java code. Now, of course, nothing really requires it to be Java, but it's just really clunky to not use Java, so everyone just uses Java. And if need be, they can, send this message out of Java to a native process at that point, just for compatibility reasons. So the way to think of these components is that you can have components of very different kinds of types. So one kind of a component is an activity. So it's basically a UI for the user. Like I launched an application, it shows up something on my screen. That's an activity component. So if I wanted to start an application, have the user start interacting with the app, I'd send a message to a component. If that component starts running, it starts drawing on my screen and starts sort of visually interacting with me. You can also have database components. In Android terminology, these are called content providers, I believe. These guys basically provide like a little SQL database that you can use to store data inside of an application. And the reason these are components is that you can now interact with them through from different applications if need be, and if allowed by some kind of a sharing policy. We'll look at that in a second. And there's a couple of other component types. There are services that just do sort of RPC operations on behalf of some other application. There's something for receiving broadcast messages, etc. But roughly, there's a couple of standard component types that Android defines, and these are the things that send and receive messages between applications. Hopefully makes some sense. Questions about this plan? Kevin?
Clarify the reference monitor and the components.
Yeah, we'll dive into these guys in a bit. Components, to clarify what these are, components are just something that receives a message. We'll look at what a message looks like in a second, but a component is really just a function in your code that will be called when a message comes in. This is very much like a TCP connection when you receive messages or incoming RPC requests to a service you might write in Lab 2, etc. The reference monitor basically has the job of taking messages in and then has a couple of things that needs to do with that message. One is that somewhat, mundanely, might actually need to start the other application. So if a message comes in for app 2, but app 2 isn't running yet, the reference monitor needs to actually start app 2 to begin with. So the reference monitor is how every single application actually starts in Android to begin with. So first, the reference monitor starts, and then the system synthesizes a message saying, oh, please send a message to the launcher. And the reference monitor starts the launcher, which is the home screen. And then the launcher, when you push an icon of some application on your phone, that'll send a message to the application's activity saying, start the application. Then the reference monitor will start that application process as well. So the reference monitor is responsible for bootstrapping all these processes and setting up the user IDs and getting them to run with the right privileges. And the reference monitor also is in charge of looking at these manifests. We'll look at them in a bit, and deciding whether the security policy in the manifest allows messages to be sent to that application or not. Question?
So for each application, I guess the components are like standardized across applications, but each application has its own set of components.
So what are these components, right? So there's 4 types of components: activity, databases, services, and broadcast receivers. But you can have 50 components if you want. Each one of them has to be one of these types. So a pretty common thing is for every kind of a screen you have in your application, you'll have a separate activity component for that screen. Like looking at, I don't know, my bank list of accounts is one activity. Looking at a specific account, that's another activity. Sending money to a friend, that's another activity. That's a different screen or UI. So that's how these things are typically structured. You'd probably have a different, maybe a component for every database that are meaningfully different, perhaps. And maybe if your application provides services for other apps, you might have multiple service components. Or maybe none, like for a purely user-facing app that has no interesting sort of data sharing plan, maybe just has a single activity. Like a flashlight app probably has one activity or one component. It's an activity component, just has a button to turn on the flashlight. That's it. All right. Other questions? Okay. So let's try to understand what these messages look like that are being sent between applications. In Android, they're called intent messages. And roughly speaking, there's 3 fields in an intent message that are being sent. One is where you want the message to go. So it's the component where you're trying, it's like the destination for your message. And it's just written as the name of the app. So for example, com.android.phone, that's the name of the app, / the name of the component, dialer. So this might be a name of a component where you might send an intent message if you want to ask the phone to call a number for you. The other part of a message is sort of in addition to a destination, you can attach an action that describes what do you want to do with this message? What are you trying to achieve? Like what kind of a sharing thing are you doing here between applications? These things are defined by the Android platform itself. So the Android platform has a bunch of verbs that describe, here's the way you could, like all the different things you could, all the ways in which you could share between applications. So one example might be main. So the main action is like pop up the top screen of the app. Like I might send a main intent to the dialer if I want the dialer app to just start running, and you could like look at the dialer and punch some numbers and dial the number. You could also send a different action like dial. So the dial action is if I want that thing to call a phone number or like dial a phone number or I don't know, Google Hangouts, whatever. Another action might be to share a document. So I might have something I want to send to a buddy. I don't actually know how. Might be email, might be a text message, might be a Facebook message, but I want to share something with a buddy or with someone else. And there's a bunch of other kind of actions that go into an intent message, but you pick one. I'm sort of listing out the options that an application might choose. And then the last thing that goes into the message is the data that you're trying to send or act on, and there's sort of a type with the data. So if I'm trying to call a phone number, I might send a message to the dialer of the type, action dial, and the data might be a URL for, I don't know, 617-253-6005. Call this number. So that's a data payload for this intent message that the recipient will get and act on. Does this make sense? So, it doesn't seem super exciting so far, but there's some really cool things going on here. The most surprising thing is that this component field is actually optional. So it's pretty common, actually, in Android to send intents without a component being specified. So these are called implicit intents. And this is a big deal for Android because it means applications can interact without knowing who's on the other end. So I might not know what phone app you're using. Are you using the Android dialer? Or are you using Skype? Or are you using some other phone service, VoIP, SIP, whatever? I can just send an action dial with this phone number to whoever wants to use to sort of, service phone calls on that user's device. Same thing with if I want to view a PDF file. I don't actually know what PDF viewer you have installed. I can just send a view action with my PDF file, see what PDF viewers are available, and the user might pick one if there's multiple. Same with sharing. I might not actually know if the user intends to share some message through a text message, through Facebook Messenger, whatever. So I don't know the component name, but I know the payload and some sort of semantic information about what I want to do in interacting with a different application. That make sense? So that's sort of a big aspect of how Android has some kind of reconfigurability or the user in control of the sharing by having a good dictionary of actions and allowing the applications to leave out the exact component destination for where messages are being sent. That make sense? Questions? Yeah. They're not necessarily all listening, so we'll see, I guess, in a second where the security comes from for which intent messages are allowed to go where. So the app actually gets to decide what messages it wants to handle potentially and what privileges it requires from the other end. Like, can anyone invoke this, or is this only accessible to certain other applications? But yeah, important to pin that down. Other questions? Yeah. So, okay, so your question is, okay, well, what goes on an iPhone? iPhone has a much more specialized set of APIs like this. I think Android has a fairly coherent, like uniform plan. Here's how every application is going to share. And even system applications, or that might look like a system app on an iPhone, like Maps, the web browser, your email client, all these things, there just happen to be some application on Android. It might come from Google, but they all play by the same rules, and they're all replaceable. They're all sort of in the same universe of component and application names. They're all using intents. My understanding, okay, partly because I can't look at the source code of iOS, I don't really understand very well. Android is nice. I can just pull it up in my browser and read it. My understanding is iOS Inc. has a much more restrictive set of APIs. They will say, oh, well, you can build a PDF viewer. That's an API. And, okay, I can plug in a PDF viewer. But it's not like I can take over how phone numbers are being dialed in a general way, or take over your address book or anything like that. I mean, maybe there's specific APIs for very specific purposes. So in another way to think of it, maybe Apple sort of picks these actions, and for the ones that they think are important, they'll design a whole API for that action. But it's much more, I think, specialized where they think it's worth having extensibility. Yeah? Can a developer create their own action types? I don't know offhand. I don't remember. The developer can create pretty much anything of their own everywhere else. It might be that the actions are a fixed universe that is a pretty big universe, but fixed. But I gotta say, don't quote me on that. It's been a while since I looked at that part of it. Yeah. Other questions? All right. So let's look at how the reference monitor decides when it's okay to send one of these intents to another application. And there, the plan is roughly around an idea called labels. So a label is just a string. Might be some string like dial perm for being able to dial your phone. And what's going on is that apps have some number of permissions associated with them. These are the positive privileges that an application has. So this application might have the permission dial perm, which is intended to reflect the fact that, this guy should be able to dial your phone. It might also have your contacts label in its privileges or permissions. And that reflects the fact that it should be able to get your contacts. And this is on the sending side. So this is the app that's going to send an intent somewhere. And then on the receiving end of an intent, the security plan revolves around individual components. So here you might have, this is our application 2. This might be the phone application, for instance. It might have this dialer component. And this specific dialer component is protected by some label. So it might say that, you must have dial perm required in order to talk to this component. So if you want to send any message to the dialer, you better have dial perm in your set of permissions. So it's sort of, you can think of it as like more tag-based rather than UID-based. The UID forms the basis of the raw isolation mechanism, but in terms of who can send messages, what's going on is applications have privileges that are called these labels. So an application can have multiple of these. And then every component is protected with one of these labels being the thing you got to have if you want to talk to this component. It might be actually that many different components have different permissions that are required. So you might have also, let's say, I don't know, here's my address book or, contacts application. And it might have an address book component. This is a database. So under the covers, of course, internally, it's going to talk to a SQL database file stored in /data/app for this application. But as far as other applications talking to it, they have to send messages to this address book component, and it might say, the required label is the contacts label if you want to talk to me. So that's the way security checks are specified to a first order, is in terms of these string labels that are tied in the positive sense to a component. These are privileges, and maybe sort of you can think in a negative sense, like the requirement on every component. Here's what you got to have to talk to it. Make sense? Questions? Yeah? Where these things are stored? Yeah, so I guess here I'm sort of drawing direct arrows, but indeed, all the arrows, like all the intents, go through the reference monitor. So reference monitor is going to sit in the middle here, and it actually pulls up these configurations from the manifest file. I guess we'll talk about that next. And the reference monitor is going to check. It's going to have a list of all the labels that every application has, all the labels that protect every component. It's going to have that stored in memory from the APK files and elsewhere, and then it's going to make that check before allowing the intent to go through. Question? Yeah, so they actually sort of went back and forth. We'll talk about that, I guess, now, where these permissions come from. The thing I'm describing now is sort of their initial plan. Everything comes from the manifest. And now they've augmented that with runtime checks. The reference monitor actually pops up on the user's screen. So let's look at actually, I guess, what's going on in one of these manifest files, because that ends up being at least a starting point for security. So there's a couple of interesting things in the manifest. One is every application in the manifest actually says what are the needed permissions for that application. So you might say, okay, well, this application is going to need the dial permission and the contacts permission. So at install time, or when the APK file is signed by the developer, it's already decided. Here's the set of permissions that the application can possibly use. And the user, when they install it on their device, can potentially examine this and decide what permissions are there. So that sort of enumerates this list. These are the positive permissions that the application needs. And then also, there's a list of components in the manifest. So, I don't know, you might have a couple of components, A, B, C, whatever. Some of these guys might just be private. So for every component, the manifest says, here's how you can share with this component. Some of them might just be internal things the application uses internally. Like inside of my banking app, there might be a component for send money to a friend. But maybe the bank doesn't want to have an API for allowing others to ask my bank to send money to someone. So that component will just be marked private. And for other components that are marked public, the manifest says, here's the permission that's needed to use this component. So maybe B, for some reason, needs dial perm in order to talk to it. That is a slightly funny example because dial perm will probably show up in a different application here, but hopefully you get the idea. And then, C also, might be public, but with a different permission. So maybe you need contacts as the permission in order to talk to C, and so on. Make sense? And then the last sort of relevant part of the manifest is there's also a bunch of what are called intent filters. So these guys basically describe, here's the kinds of intents that each component is willing to handle. So that's for implicit intents. So you might have intent filters that say, B can handle, maybe view intents for PDF type files. And that basically means that's a PDF viewer. This example doesn't make a whole lot of sense. Like, a PDF viewer probably wouldn't have a dial perm permission, but so be it. So that defines how the app wants to provide services to other applications. So if you install, some alternative mapping application like Waze instead of Google Maps, you're going to have an intent filter saying, I'm willing to have map intents handled by Waze now. And then the user can choose which application they want to use. Make sense? So in terms of security, now we have to, of course, answer the question, when is it okay to send an intent? We sort of have a set of rules already, which is the intent can be sent if the recipient's label is present in the sender's set of permissions. But so where does the user get to decide this? So the user approval, if you will, comes in two stages. So the first stage is at install time. You can actually look at what are all the permissions that the application is asking for. This is actually, initially Android just did this. So when you install an application, it said, this application is going to be able to dial your phone, take it or leave it. And, better than nothing, I suppose. But as the paper suggests, turns out the users have a hard time deciding if that's okay or not. So Android, over time, added the second approval process, which is on top of installation. At installation, you do sort of see these permissions. They're not super prominent, I think, anymore, but they do get recorded. But then the first time the application tries to use a permission, the reference monitor will actually prompt the user. So the reference monitor prompts at use time and tells the user, here, this application is trying to use this permission. Do you want to allow this or not? And it's actually quite useful that the reference monitor is in the middle of the message flow here, because it gets this message from an application that's trying to send something somewhere. And this guy is now a trusted component, can pop up a message to the user saying, do you allow this or not? And then if the user says yes, and the manifest allows us, then forward it on. Make sense? Questions about how this manifest and sort of user approval works here? Yeah. I think the way this, the question is it only the first time? I think what Android does these days is the first time so there's in order to use a permission, an app needs to have sort of active user approval of that permission. So initially it has no such approval. So when it sends a message, when it sends an intent, the user gets prompted, and the user can either say, allow it just this time, and then next time you'll get another prompt, or you can say, keep allowing this in the future, either whenever the app is running in the foreground, or even if it's in the background, etc. But, yeah. Other questions? Yeah? Can the user approval be bypassed by the developer or faked? I guess that would be a bug in Android, so certainly the design of Android is that this should not be possible. I guess for this whole discussion, for this lecture, we're assuming that the Linux kernel and all the stuff underneath of Android is correctly implemented. Of course, there's going to be bugs, but sort of, for sanity's sake, we're going to discuss the sort of plan above the kernel separate, and then, of course, you'll have to worry about security of the kernel at some point, but they're pretty orthogonal. Like, if it's a kernel bug, yes, it's a kernel bug. It can subvert anything, but if there's no kernel bugs, this is the plan. I guess by kernel I also mean like the whole framework, like the reference monitor also has to have no bugs in how it pops up this dialog box for the user. You got a question? Okay, so one question is, can apps share their permissions with other applications? So in Android, the answer is sort of no, which is maybe a little bit weird or quite different from how it looks in Linux, right? So in Linux, if I have access to a file, I can call chmod and make it world writable. You can now write to it. No problem. In Android, that's not the case. So the manifests are stored in the reference monitor. You can't change them. Now, of course, nothing stops one application from proxying requests from another application. So if one application has dial perm and can call the phone, it can expose its own service to other applications. And there's no requirement that that service requires dial perm in its own right. But, yeah, okay, so that's how it works, yeah. There's some question over here. Yeah. So the question is, if I say allow, this app to call the phone, and I say, remember this forever, what happens is, actually, when I'm interacting with that screen and touching buttons, I'm interacting with the reference monitor. And the reference monitor has its own config file that is stored on disk, that's sort of separate from any app, and separate from those APK files. There's just like the reference monitor config file. And when I tell it to remember some user approval, it saves to its config file. It's probably like a SQL database, but saves there, and that's where it lives. And I mean, in principle, you could probably pull up some settings menu and revoke it if you wanted to as well. Other questions? All right. So that's sort of where the permissions come from. One interesting thing is sort of where these strings come from. So dial, perm, and contacts. So we were talking about some strings are special, like these actions. That might actually be the case. Turns out that the labels, things like dial, perm, and contacts, are actually application defined in Android. Like it's a really pretty egalitarian framework that apps can do pretty much anything that the system themselves can do, subject to the user choosing to use that. So the applications can actually define these permission labels. And this is sort of another part of the last part of the manifest we'll talk about, which is that in the manifest, you can actually have a section saying, this application defines a new label. So like a new kind of permission that applications might want and that components might require. So just to make up some example that might be at least halfway realistic, it might be that the Facebook application might define its own label, like com.fb.addFriend. So it might be that the Facebook app wants to allow other apps to add a buddy to your Facebook account. And maybe they don't want anyone on the phone to be able to add buddies because then you'll install malware that adds 1,000 friends to your Facebook account. But they want Android to help mediate who can actually ask to add a friend to your Facebook account or not. So in the Facebook app, they can actually say, I'm defining a new label now. And when you define a label, there's sort of a couple of things that go along with it, on top of just saying, okay, well, here's a string. It exists now. You get to actually specify what type of permission it is, and the type controls who can actually get it, who can ask for this permission. And the other is you get to specify some kind of a user description. And the description is important because the user, at the end of the day, is going to be in charge of deciding whether any particular app can get the add-Fred permission or not. So the description of a permission is what you see at install time. If I pull up an app and it says, the app is asking for dial perm, I'm not going to look at the string dial perm. That's kind of, well, maybe I can guess, but not super meaningful to a user. What I'm going to be looking at is the description of that label as defined by the manifest of the app that cooked up that label in the first place. And that description is also going to be popped up for me at runtime. So if an application wants to use the dial perm permission or wants to use this add friend permission from Facebook's app, the reference monitor is going to pop a dialog box saying, this app is trying to use the add friend permission. Here's what it means. It's going to give me the description from Facebook, and then I'll say yes or no. Do I want to allow this app to use add friend, the permission? Make sense? So once some application defines a new permission label, any other component can protect itself with add friend. So Facebook's own components can protect themselves with this add friend permission. Other applications can choose to do so if they want, etc. So there's no restriction in terms of who can protect themselves with a label. But there are some restrictions in terms of who can get this label as a privilege. So there's basically, well, three types of labels in terms of sort of their severity, if you will. There's this oddly named thing called normal, which is basically kind of harmless, if you will. I'll talk about this in a second. There's dangerous, and then there's signature as a permission type. So these three types of permission, the idea is that normal permissions are really benign stuff that you don't even need to ask at install time. It's like, change the wallpaper on your phone. That's a normal permission. And the reason for having normal permissions is so that you can retroactively audit, figure out who the hell changed my background on my phone. I can go through the apps and see, who has the change the background permission. But it's not super important to prevent upfront. The dangerous permissions are sort of the main things we would sort of talk about here. Like, I don't know, send an SMS message on my phone, dial someone, read my contacts. These are permissions that you want to proactively protect against. And these are the kinds of things that you might either be asked at install time. Do you really want to install an app that's going to have this permission with this description? Or at runtime, when it tries to use the permission, it'll ask me from the reference monitor. And these signature type of permissions are kind of an interesting thing in Android. Signature permissions are basically some internal permission type for an application developer. So the idea for a signature type of permission is that only apps from the same developer can ask for this permission. So in the case of Facebook's add friend permission, for example, this would mean that if we make it a signature type permission, only other apps signed by Facebook's key can possibly ask for that permission. No one else can even ask. So the user can't even screw up by accidentally saying yes. Any guesses why this is a good idea at all? Where this might be useful? Seems like a slightly weird constraint. So I think what's, I guess.
Maybe the Facebook example, like maybe we want people to use Instagram to become the platform.
Yeah, so one way to think of it is that, so the reason for these signature permissions is to allow the developer to define, like, here's the set of applications that can use this application, this permission, no one else. So maybe your example is Instagram or other Facebook apps, perhaps. Another way to think of it is if an app developer wants to privilege separate their own application to multiple components, the way to do this on Android is you just publish a bunch of little apps, and they talk to each other, very much like you would have seen in RLBox or in OKWS, and you need to control which of your app components can talk to which other app components. And you don't want the user to accidentally say, someone else can also talk to your intermediate internal component. That would be a silly thing to do. So I think there you use a signature permission. It basically says the user is not in charge of handing this out. I'm in charge as the developer. And then if you sign all your app components with the same key, then they can all talk to each other, subject to your manifest. But the user can't accidentally give away that permission. So I think those maybe two use cases are sort of either the walled garden of Facebook use case or sort of privilege separation, the developer wanting to control interaction between their own parts are probably where you'd see the signature permissions being used. Question back there? Yeah, exactly. So, okay, so doesn't that couple the applications together very tightly? So indeed, yeah. So these signature permissions are not an example of where you can all of a sudden have the user supply a different component or application, right? So this is not a case where you'd have, like I choose a different PDF viewer. So you wouldn't be using that here. So signature permissions are really intended for the app developer probably either knows now or will be the only one supplying the other components that talk to this protocol or interact. Yeah, so it's really for some internal structuring where the developer finds it useful to use Android separation between their own app components or parts or sub-apps, whatever it is. Yeah. Any other questions here? All right. So that's where these permission labels come from. So you can sort of see it's actually kind of a cool design. I mean, we're sort of looking at various angles of this. Not everything here is, I guess, super important, but it's interesting to see how they've cooked up a framework where most things, even sort of the kinds of permissions you can ask for themselves, are defined by applications. So you really can have a new developer come around and, if the user wants to, they can sort of replace all the almost Android components with components from a different developer. It'll still all work and still have all the same security benefits because they can use all the same egalitarian mechanisms from the framework. It's not, almost nothing is really tied to Google or Android being sort of more trustworthy than any other application developer here. Make sense? All right, so let's look at, I guess, a couple of things going on with the reference monitor and try to understand what are the limits of the reference monitor, where is it sort of capturing a security policy and where is it not quite capturing a security policy we need. So why is this reference monitor a good idea for security at all? Why do we need this guy? I mean, we could just do stuff like just have a network and have these guys listen on TCP ports. You can talk to an app. If an app doesn't want to talk to you, it'll drop your message. Why do we need a reference monitor in the middle, mediating all this stuff? Yeah? Uh-huh. Yeah, so one, I guess, nice thing about the reference monitor is that you might say, okay, it's like protects the buggy apps. So if you want to build a secure Android application, you don't necessarily have to write bulletproof code that's going to reject all bad messages. You just have to write a policy in the reference monitor that says, I don't want to talk to anyone. And that's good enough. If you say that policy and the reference monitor is good, that's all you need to do for security. So it helps sort of outsource the problem of defending against arbitrary messages. Another, I guess, important thing is that, to some extent, there's some interplay between security versus user choice. What I mean by this is that if you're sending an implicit intent somewhere, the reference monitor is the one that actually has to figure out where is this going. So I send some message saying I want to open this PDF viewer, then it's the reference monitor's job to find me another application that's capable of viewing a PDF file, for example. And the reference monitor can actually take security into consideration there and actually find me an application that's willing to take this intent message subject to the labels on the receiving component. Maybe there's some PDF viewer that's not willing to talk to with a web browser because it doesn't want to have arbitrary PDF files coming from anywhere. So then the reference monitor is just going to pick a different PDF viewer. So there's some interplay actually between security and intent routing here. So it's good to have the reference monitor there. And I guess the other thing that we already saw is that we might actually need to get user approval. So it would be a mess if a receiving application got an intent and now has to pop up a message saying, oh yeah, I started this PDF viewer. Do you actually want to accept this message from this other app? That would be pretty strange. So instead, it's nice that the reference monitor is sitting in the middle here and prompting the user in a consistent way, and also, I guess, protecting buggy apps by having a trusted UI for the users to decide whether to allow particular operations or not. Make sense? So in general, this reference monitor pattern should probably remind you of what we saw in the Google paper, where, in the Google paper, they had this RPC system that was underlying the whole data center and played a pretty similar role where different services in Google would send messages, RPCs to each other, and this RPC system decided which things were allowed or not. And the reference monitor plays a somewhat similar role here at the phone, of course at a much smaller scale, but same logical operation going on. And one nice thing going on here, sort of an example of mandatory access control. So what mandatory access control means is that there's a policy that's specified by the developer, And it's not up to the application to enforce that policy. So it's not up to the app code to decide which intents to receive or how to process them. There's a manifest file that says, here's what's allowed, here's what's not. The nice thing about it is you can read it and decide, oh, well, is that good or not? Instead, it might be difficult to look at the source code of an application and decide, in what cases is it going to accept a message or not. So having this declarative policy is one nice thing in general of these kinds of mandatory access control schemes. Like easier to audit. And I think this is also true in the Google design too, where you can look at the whole data center and say, oh, well, here's who can talk to whom. I can get a pretty good idea of security at a top level without having to dive into the C++ code. Make sense? All right, questions? All right, so let's look at maybe a couple of situations where this reference monitor plan doesn't quite work out in Android in the sense that it's not able to do all the security checks in the reference monitor. Somewhere else, security policies are being specified. So one example of where this reference monitor security checking model falls apart to some extent is in the case of broadcast messages. So here's what I mean by this. There's a notion in Android of a broadcast intents, which are kind of like broadcast messages being sent to any application in the system. So a pretty common example of this might be you have your phone application running on Android, and when the phone app receives an SMS message from the cell phone network, it needs to give it to someone that actually cares. That's going to display to the user, and the user can then decide what to do with the text message, read it, respond, whatever. So the way this happens is the phone application actually sends an intent message. And it's actually a broadcast intent. The reason for this is that this is in contrast with sort of usual intent messages being intended for one application. So the user chooses, here's where this message should go. If I want to open a PDF file, I don't want to run every single PDF viewer just in case. I just want one. That's good enough. But for incoming SMS messages, it might make more sense for this SMS message to be delivered to every application that might be handling your SMS messages, because you don't want the user to get a pop-up saying, oh, an SMS message come in. Which application would you like to read it in? It's like not a great user experience by, I guess, the designer's plan. So they have this notion of a broadcast intent, which, of course, as everything goes to the reference monitor, but then the reference monitor actually fans it out and sends it to every application whose intent filter allows or wants to take this message. So this way that's actually how many of these two-factor apps on Android work. They actually register themselves as broadcast intent receivers, and then when you get a two-factor SMS code coming in, this other application will get a copy of your incoming SMS message, and it'll just authenticate you with two-factor without you ever having to even copy-paste that number in there. Kind of convenient, but also slightly worrisome because every app can potentially do this. But so that's sort of the machinery underlying this. And this sort of turns out to not quite work with this manifest-based definition of the security rules here, because if we look at what the rule is, the rule really says the sender has some privileges and the receiver gets to say yes or no. But here, the sensitive data is really inside of the message. So here's, this is an SMS received type message. Let's say that's the action type. And the payload is a sensitive thing. But thinking of it in terms of the usual intent rules doesn't really fit well. It's almost like the phone app has to prove that, oh yeah, I'm allowed to give you an SMS message. But if you think of it in terms of the confidentiality of the SMS message, you actually want it the other way around. The receiving app should prove that it's good enough to receive your message. And that's not the way these component rules work out. So Android actually added an extra field to an intent, which is sort of you can put a requires statement, if you will, on an intent message. And if the phone app wants to broadcast an SMS message to your phone, it'll say, oh, the receiver must have the receive SMS permission. So this now looks sort of almost the flip side of the security check we've had so far. So instead of checking that the recipient's label is allowed for the sender, this check checks that the receiving application has the permission of this label that the sender chose. Does this make some sense? Slightly complicated explanation, perhaps. Yeah? Sorry, this is the action for the action of the intent. This is like the kind of intent it is. But typically, if we don't add this extra rule, then the security rule that the reference monitor will check is that the label protecting the receiver is in the sender's set of labels. Because that's the rule, right? Like, in order to send to a component, you have to be allowed to send there. But here, one the other way around. Like, you're allowed to receive it instead of I am allowed to send it. So the big difference here is that for the previous check that you're allowed to, for the previous check where the reference monitor is checking that I'm allowed to send you something, that whole thing is written in the manifest file. No code is required. I don't have to read your code to understand whether you got this check right. But here, all of a sudden, I have to read the code because the manifest doesn't say that these kinds of messages go with this permission. It's really the sender that when they send an intent, they have to tag it with an extra field saying, oh, well, this is a broadcast message, only give it to apps that have this particular permission. So now this is sort of, edging on the limits of where you can really define the whole policy in the manifest file versus now the code of the application is involved in setting the policy. So now the phone app better set this field in its implementation on all the outgoing intents. So just to highlight, like, so some of these dynamic, basically, kinds of checks or things that don't fit in the original model, well, now you have to rely on applications, and you don't get quite the same benefits of the reference monitor in terms of, guarding against buggy apps, being able to audit this, etc. Make sense? Other questions? All right. So another really important case where this manifest doesn't quite work out is in terms of dynamic permissions. So here's what I mean by dynamic permissions. It might be that the application that needs a permission didn't actually know it at install time. So let me draw an example of what this looks like. So delegation is the general problem that I want to talk about here. So you might have an application like maybe the Gmail app that is running on my phone. And the Gmail app has a database, a component, storage component, of all the attachments for email messages. And the Gmail app might want to allow the user to view an attachment, like a PDF file. So what's going to happen is the Gmail app is going to send an intent saying this is, here's the action is probably view, to view some data. The data is, here's the URL. It's, content, attachments, /5. It's like the 5th attachment of this database. That's the way you send data, is through sort of pointers or URLs in Android. And then some application, after this goes through the reference monitor, this goes to the user's chosen PDF viewer. So the PDF viewer now needs to fetch the actual PDF data out of this attachments database. But it doesn't know that it needed that permission to begin with. Actually has no idea what permissions it's going to need before it even starts running. So maybe this is like a permission to get the attachments for email messages that you would need. Or if you're using it to view something from a web browser downloads folder, that's a different permission that the PDF viewer is going to need. So at install time, the PDF viewer has no idea what permissions it's going to need because the permissions depend on who is asking or who sends the data to view. So the way this works actually in Android is that the reference monitor has a list of what's called pending intents. So that's the mechanism that Reference Monitor supports. And the idea is that when the Gmail app sends an intent saying, I want someone to view this PDF URL, it also tells the Reference Monitor, whoever wants to view this PDF URL, give them the ability to send this kind of an intent back to me. So you can register sort of callbacks into the Gmail application with the Reference Monitor, allowing whoever got this intent message to call you back. So this is a dynamic kind of a permission. It's not allowed by the manifest at install time, but it's allowed because the sending application said, yeah, give it to whoever wants it. So the Reference Monitor actually has a table of pending intents, and you can register them when you send an intent to someone else, and that's going to allow the PDF viewer to now go back and query the attachment from Gmail's database of attachments. That make sense? So there's sort of extensions to Android's static-ish manifest security plan that allow you to allow applications to specify some kinds of permissions at runtime. This turns out to be important for certain kinds of delegations or sharing patterns where the exact apps aren't known up front. Does that make sense? Question?
The way you explained it is so the email application endows this PDF viewer with the ability to fetch the data.
Yeah. Right.
But how is this a callback? Like, is the PDF viewer actually like transfer control to Gmail or something?
So okay, so your question is like, why just say callback? It's like a logical callback. It's not necessarily a callback in the sense of RL box, the way we look there. It's not a direct jump. What's going to happen is the PDF viewer is going to send an intent message back, or doesn't even, not necessarily even back. It just, the PDF viewer is going to try to do a fetch. The way you do it is you send an intent message. The Reference Monitor is going to look at this table and say, oh yeah, that's one of the allowed things in the exception table. I'll let it through, even though I wouldn't have allowed it before. Then it's going to let it through and let it fetch the data from Gmail. Yeah. Same way that, for example, okay, this example might seem a little bit contrived because why didn't you just send a copy of the data to begin with there? So for read-only things, you could imagine now just like send the data with the request. You don't even need this pending intent mechanism. But it might be useful if you want the viewer to edit something. So maybe in the Gmail case, this is not true, but if I have the Google Drive app and I want to edit an Excel file stored in Google Drive, I might open my Excel editor for spreadsheets, it'll edit it and be able to save it back. And it's able to save it back because I opened it. That's what gives it the right to save it back. And it's not just sending data one way now. Make sense? Other questions about this model? So these are sort of to give you some flavor of Android having sort of a combination of both this mandatory access control model where the manifest defines everything, but also some runtime things like delegation and those sort of broadcast intent rules that get specified. All right, so I guess what else is going on Android? So more sort of, now pulling back from the device itself. There's also a fair bit of stuff going on outside of the device. So the paper talks about off-device security as well. So initially, actually, they just had the device-centric plan we've talked about so far, where the phone is responsible for isolating applications and enforcing policies. But one way in which things go wrong in Android, or at least in the initial versions of Android, is that the user was really in charge of making too many decisions. It was very easy to do something wrong. I don't know, very easy, but better than Windows, I suppose. But very easy, or easy for an application for a user to approve something that was detrimental at the end of the day. So one thing that Google added was actually this service. I think it's called Google Play Protect. And the idea there is that Google actually runs a bunch of servers that are going to check and audit various APK files, applications that a user might want to install. So this is like the App Store for Android. And the default rule, the device now has a mode where it'll only install for applications that come from this App Store that have been approved by Google's Play Protect thing. So this allows Google to filter out applications that kind of, look like spam, if you will. So these are maybe not applications that violate any hard policy, but maybe these are just nuisance apps, or that Google can sort of analyze a whole bunch of apps and say, oh, they're all the same thing. They're all trying to attack you in some way. And this, I think, has been reasonably effective at reducing some kinds of attacks on Android devices. Now, one nice thing is that actually this is a feature that a user can opt out of. So this is a setting by default on an Android phone. You will always be required, you will be required to install apps only from this App Store, but as a user of the device, I can disable this, and then I can go to the more sort of device-centric security model, and I can install any app I want. So in contrast, I guess iOS doesn't give the user the switch. In iOS, the switch is always enabled. iPhone devices will only install from the App Store, for better or worse. Make sense? So that's one sort of extension that Google had to add on top of Android to deal with certain kinds of more sort of, I think, spam-oriented phishing applications, perhaps. Make sense? So where are the, I guess one interesting thing to talk about is where are the security problems. If you had to attack a smartphone, I guess Google or iPhone, or Android and iPhone, doesn't really matter. Where are the weaknesses in these kinds of, on the applications front? Where would the security problems be? Yeah. Oh yeah, question, yeah. How do they verify applications? I think they look at manifests, they look at what permissions you're asking for, they have some patterns they look for, whether there's a sensible, are you asking for too much? They actually will run your application in an emulator on their servers and see what the application is doing. And they have some rules for what looks suspicious, and maybe they'll manually review it. If you're maybe fuzzing the kernel and trying to invoke syscalls with funny arguments, maybe they're not going to allow that application on the user device, etc. Make sense? All right, so coming back to the security question. So where are the weaknesses of this application model? Yeah. I'm sorry? Yeah, okay, so maybe the reference monitor has bugs in it. Plausibly, yeah. Or I guess at that rate, like anything, right? Like Linux kernel. Like the whole trusted computing base, the whole Android platform needs to be correct to some extent, and Linux kernel is certainly part of it. Has to be right. Reference monitor, hugely important. Yeah. Where else would you look for problems? Yeah. Yeah, so like malicious apps. So it's kind of interesting, right? Like the goal was to handle malicious apps to begin with, and they handle them to some degree, but if the user really installs this malicious apps, if the user installs a malicious application, the malicious app can't corrupt other apps' data. But if the user willingly gives their data to this malicious application, that's something that Android doesn't really have a plan for. So if you install, a malicious PDF viewer that sends your PDFs to somewhere else, that would be not something Android will help you with. If you install, the wrong bank for MIT's credit union, well, you typed in your password into this app, you thought it was the MIT FCU, but it came from somewhere else. These are tricky questions. I think these are the kinds of problems that I think they try to protect with this centralized service, the Google Play Protect thing. Because they have global visibility. If they see that some developer is publishing 50 different bank applications that might look suspect, maybe they'll suspect you're phishing for credentials for bank accounts. But yeah, this is a tricky one. Other places where problems might arise, yeah? Yeah, so maybe like DOS attacks, yeah, potentially. So I guess in general, like one security problem that Android struggles with and iOS struggles with is battery life. So application developers aren't really incentivized to give you a good battery life. They'll just spin in the background, chew up your battery. And I'm not sure, I guess you mentioned specifically sending lots of spam to the reference monitor. If the reference monitor doesn't have bugs, it'll just keep responding no to the spam. But in general, I think one thing that Android has been doing more of is designing APIs where they will control the power use that an app is allowed to have. So they'll actually think of using the battery's energy as more of a security concern, perhaps more than they would have initially. Yeah, so that's probably a reasonable plan. Yeah, sort of user mistakes, as we guess, is another place where problems still happen. So even, on Android, iOS doesn't really matter. The user might accidentally give the data to the wrong application. Sort of maybe kind of the same issue as that, perhaps. But the user is still, I think, a significant weakness point of this, and sort of comes in together with the fact that this is a general purpose device. If you had two phones and you had work on one and the home stuff on the other, you wouldn't get them confused so much. But I think the fact that everything is on one device makes it perhaps easier for the user to get them confused. So the whole goal of enabling sharing is fundamentally to some degree at odds with the user screwing this up, because the user is now in charge of sharing. All right, so that's all the sort of, I think, technical discussion I had for Android. In general, that's, I think, probably one of the better case studies of how to do isolation and sharing together. Actually, has been pretty successful at enabling all kinds of cool stuff you wouldn't have been able to do before. And, for better or worse, lets users actually decide their security policy. All right, so that's it for mobile phone security. We'll look at a new topic, finding bugs, next Tuesday. See you guys then.